What's up, nerds? So today we're going to go over separation of variables, also known as separable ordinary differential equations. So this is another technique used to solve first-order differential equations, but a lot of times we'll use it for ones that aren't linear. So linear ones we'll use integrating factors. For this we'll use separation of variables. Separable ODEs can be written as f of y times y prime equals g of x. So you could write it as one function entirely of y times y prime equals another function which is just a function of x. So we'll do a bunch of examples so y'all could get the feel of this. Before we jump into any examples, let's do a refresher on chain rule. So if you take the derivative of y squared, where y is any function, and we're taking the derivative with respect to x, you'll get 2y times the derivative of y. And so if we have 2y times the derivative of y is equal to x, then integrating both sides with respect to x, we get, by the fundamental theorem of calculus, that y squared equals x squared over 2 plus c. So then we could just solve for y and get y equals plus or minus square root of x squared over 2 plus c. So if you need to pause and think about why the differential equation 2y prime equal to x has this solution and why the fundamental theorem of calculus works this way, take a second to think about reversing chain rule. So let's take a look at maybe a unique solution, have some initial conditions like y of 2 equals 1. And so plugging this in, we're only looking at the positive square root because we have y is equal to a positive value. So plugging in 1 for our y, we get 1 equals square root of 2 squared over 2 plus c. And then we could solve for c, squaring both sides and then subtracting 2. And so we get c equals negative 1. And now let's check that this is actually a solution. So if we take the derivative, we get by power rule and then chain rule that y prime is 1 over 2 square root of x squared over 2 plus c, and then times the derivative of x squared over 2 plus c, which is just x. And so plugging this in into 2y prime equals, we'll get 2 times y times, and then our y prime is x over 2y, and we get that the 2's cancels out, and then the y's cancel out, and all we're left with is x. And that's exactly what the ordinary differential equation said. 2y prime equals x. Again, if there are any parts that you're a little fuzzy about, you should pause and think about why it might hold. Alright, let's start our second example. Here we have y prime equals x over y, and we want to get it of the form f of y times y prime equals g of x, so we multiply both sides by y and get y times y prime equals x. Then we integrate both sides with respect to x, and you might want to stare at this for a while just to think about what the antiderivative of the left side is, and you should get that it's y squared over 2. Now again, if you need a second to pause and think about why it's y squared over 2, you could always reverse the operation and take the derivative of y squared over 2, and you'll see that you get y times y prime. Then our antiderivative of the right side is just x squared over 2 plus c. If we take this whole equation and multiply by 2, we get y squared equals x squared plus c prime, where c prime is 2 times c. But a very common trick in differential equations is when you have a constant and then you multiply it by another constant and neither of them is specified yet, you could just keep it as c. So we don't need the c prime, and we could just relabel this as c. So taking square roots, we get the solution to this differential equation, y equals square root of x squared plus c. It's plus or minus square root of x squared plus c. And we should always check our work, so if we take the derivative of both sides, well, by chain rule and power rule, the derivative of y is 1 over 2 times square root of x squared plus c, and then that times the derivative of x squared plus c, which is 2x. So simplifying, it's just x over square root of x squared plus c. And you just stare at this for long enough, and you realize it's exactly x over y. So this indeed does satisfy your differential equation. And you might be given initial conditions like y of 0 equals 2. Then you just plug in 2 in for y and 0 for x. and we get that, in this case, c equals 4, and that would give us a unique solution. As always, if there are any parts that you're unclear about, pause the video and check your work just to make sure you understand it. Let's do another basic example, this time y prime equals xy. Now you might notice that this is linear and we could use integrating factors on it, but let's use separation of variables techniques just to get a good hang of it. So again, we want to get it of the form f of y times y prime equals g of x. So in order to do that, we want to divide both sides by y, and we get y prime over y equals x. Then when we integrate both sides with respect to x, the antiderivative of the left side will be ln of y. So maybe pause and think about why the antiderivative of that is ln of y, and you could always take the derivative of both sides just to see that you indeed recover the original equation. So now we have ln of y equals x squared over 2 plus c, and then when we exponentiate, we get y equals e to the x squared over 2 plus c, and we could rewrite that as a e to the x squared over 2. And this is exactly what you would get if you did integrating factors. Again, if we check our work, take the derivative, we get that it's a e to the x squared over 2 times the derivative of that exponent, which is just x. And so y prime is just exactly equal to x times this term is y. And if you have initial conditions like y of 0 equals 10, then you just plug it in and you'll see immediately that you get a equals 10. So we've done a few basic examples now, and I think we're ready to look at the general version. So our general strategy, as you see, is to get our differential equation to look like f of y times y prime equals g of x. And then when we integrate both sides with respect to x, the left side looks like the chain rule of some function. So you could see this maybe by recalling that the derivative of y is y prime. So we could treat this integral as if we're just integrating with respect to y. And another way to see this is if you do a u sub with u equal to y, then our du equals y prime dx. Okay, so pause and think about that. And then after that u sub, our integral becomes integral of f of u du. So I highly suggest looking back at the previous examples to see how this worked. And once you're done with that, we can move on to some more challenging examples. Let's go through a few more examples, maybe do another easy one. So here we have y prime equals x over 3y squared. And again, as we just saw, we want to get it out of the form f of y times y prime equals g of x. So we could move just the y squared over, but might as well move all of 3y squared over. So we have 3y squared times y prime equals x. And we integrate both sides, and we get y cubed equals x squared over 2 plus c. And taking the cube root, we get y equals the cube root of x squared over 2 plus c. And that's our general solution. We should always check it. So taking the derivative, we get 1 over 3 times the cube root of x squared over 2 plus c, all that squared, and then times the derivative of the inside, so 2x over 2. And so if we plug this into 3y squared times y prime, we get 3 times y squared times x over 3y squared. And so the y squareds cancel with each other, and the 3's cancel with each other, and we're just left with x, which is great. And you might have initial conditions like y of 2 equals 2, and you just plug that in. 2 for y, 2 for x, and you end up with c equals 6 in this case. Let's do one last example. This one's going to be a little bit trickier. It's one that we've seen before when we were doing slope fields, and we'll see again when we do some modeling problems. So we have y prime equals y times 1 minus y. And it doesn't look like there are any x's, but if we just divide by a y times 1 minus y, then our left side is a function of y times y prime, and our right side is just 1, which is a function of x. So now we just integrate both sides with respect to y, and integrating this left side is a little bit tricky. You might remember how to do it from your calculus days. It requires the technique called partial fraction decomposition. So So we could write this integrand as y prime over y plus y prime over 1 minus y. Now again, if need be, just pause the video and check why this is true. And if you need to brush up on your partial fraction decomposition, that's okay too. Now this is in a form that's a lot easier to integrate. So the antiderivative of the left-hand side is just ln of y plus negative ln of 1 minus y. And then the right side is just x plus c. And using logarithmic rules, we could rewrite this left side as ln of y over 1 minus y. And then we could exponentiate both sides to get y over 1 minus y equals e to the x plus c, or a e to the x. This example is not like the others where it's not obvious how to solve for y. For the other ones, we would just take the square root or cube root or something easy algebraically. This left side, you still have to do some algebra, so there are a lot of ways to do it, but I think that one of the simplest ones is just do polynomial division. So rewrite this left side as negative 1 plus 1 over 1 minus y. And our right side's the same. And then we add 1 to both sides, and we get 1 over 1 minus y equals a to the x plus 1. And then we just flip both sides, and we get 1 minus y equals 1 over a e to the x plus 1. And then a little bit more algebra shows that y equals 1 minus 1 over a e to the x plus 1. Or if you want to get it all as one fraction, it's a e to the x over a e to the x plus 1. And we'll see this equation again next time. Hope you all enjoyed this video. If you did, make sure to smash that like button and subscribe. And if you have any questions or comments, drop them below. And thanks for tuning in.